Hello, and welcome to Theater to the Cosmos Coffee. Grab yourself a cup of coffee as we talk about cosmology. So, typically, I will pick a topic I see in the news, or maybe just a topic I feel like would be good to talk about. Today, it's a little bit of both. Um, we're going to talk about the crisis in cosmology. That sounds fantastic. It's really not that crazy, but it's also known as the Hubble Tension. And the reason I chose this was because it's a topic I remember from when I was in grad school. It was just starting to become a thing, and lately it's come into the news, and so I thought it'd be worth talking about. So I did a real quick, Google Ngram viewer here. Blue line here is crisis in cosmology. You can see that's had an uptick in the last 5 years, as well as Hubble Tension since about 2015. So, when I was in grad school, was back here in the kind of the late noughts. Um, so it was talked about, but not nearly as much as it is today. I thought it was interesting. There's a peak here in 1960 and one here in the mid 90s. The mid 90s is when we discovered dark energy, and I think really this crisis in cosmology topic started. I think it evolved into what we're talking about today. The 1960s, from what I could tell, that's more attributed to Fred Hoyle and some of his objections to the Big Bang cosmology. But that's not part of this topic, so we'll move on. A couple years ago, there was a set of articles here on Big Think talking about this crisis in cosmology. Um, that might be a good place. I'm not going to go through all of these articles, but it might be a good place to start. But basically, what is the crisis in cosmology? Um, Essentially, it's as we move into what some people call the era of precision cosmology, meaning our theories and our technology has evolved enough that we can really get precise measurements of different cosmological parameters. We can narrow down the constants in our cosmological theory. So, again, this is coming from a Big Bang perspective. Um, so there's things like the Hubble constant, which is what we're going to focus on now. But what I was seeing in grad school was talking about dark energy and some of the the energy density, matter density of the universe, things that would fold into um, the dark energy. Not really the dark energy constant. What's the word I'm looking for? The cosmological constant, which some people connected to dark energy. But here we're going to talk more about the Hubble constant, which I'll explain what that is here in a second. But essentially, there were two methods of determining the Hubble constant. One is using the universe nearby to look at the expansion of the universe and from there derive how fast or slow the universe is expanding. And the other was to use the cosmic microwave background, which, according to Big Bang standard cosmology, is the earliest light we can see in the universe. And basically looking at that and evolving things in time through models to today and going the other direction to get the expansion rate of the universe. So, what is the Hubble constant? So here, Big Think shows the simple formula. So when Edwin Hubble in 1929 published his paper, what he saw was that the further out galaxies are in the universe, the faster away they're moving from us. And I'm not going to. There's a lot of physics in today's topic. I'm only going to hit the surface because I really want to keep this short and sweet. But essentially, through the light coming from those galaxies, you see a red shift or a blue shift, depending on if it's moving away or moving towards you, the observer. And what Hubble saw was everything was, well, mainly everything was moving away, and the further away it was, the faster it was moving away. And that's the essence of Hubble's law. It's a simple equation: v for velocity, d for distance, and this h0, or if you want to sound British and more intelligent, h naught, is the Hubble constant. Now, we found that the Hubble constant is, well, not constant, but we still call it the Hubble constant because that's how astronomers work. But one of the big things back, kind of right about the time I was in grad school to a little bit before, was narrowing down what is the Hubble constant. What is that value? Um, and and there's different ways to do that. And actually, let's just jump to that. There's this really nice. It's an oldie but a goodie. Nice little article on the Harvard Center for Astrophysics website, talking about the Hubble constant and how we come up with it. Um, this was in preparation for the Hubble Space Telescope Key project on extragalactic distance scale. Easy for me to say. Um, and just because there was a lot of back and forth, we'll say, on what the Hubble constant was. So this graph here, let me see. No, just leave it. So this graph here is some of the earliest measurements of the Hubble constant. So Hubble himself, in his first paper, is right here. He measured the Hubble constant to be over 600 kilometers per second per megaparsec. Let me pause there. Those are some weird units on the Hubble constant. So kilometers per second, that's a velocity, a speed. And then the megaparsecs, that is a measure of distance, how far away we are, or the galaxy is from us. So a parsec is a little over 4 light years. So a megaparsec is a million light years. So 4 million light years, essentially. So that's what those units mean. So it's basically speed, how the speed changes with distance from us. And notice, Hubble measured it over 600. We get some of these other measurements right in here. And it might say who down here. So John Oort measured a value of 290. It looks like Hubble got another one at 500. Oh, okay. So I misspoke here. So Hubble in 1929 found 500. So I don't remember where this 600 value comes from. Is it Lemaitre? Oh, here, yeah. First point is from Lemaitre in 27. Okay, either way, Hubble got a little over 500. Lemaitre got 600. Notice how all of these values kind of cluster together in the beginning. And then it sort of slowly comes down and reaches almost like an asymptote here. This is a phenomenon in science called tracking. And this is something we really have to be careful of as scientists. And it's really easy to do. Today the Hubble constant accepted value by most people is somewhere in the neighborhood of 70. We'll get into that in a minute. But 500 to 70 is a big leap. So let's say I was an astronomer back in the 1920s, 30s, 40s, and I got a value of 70 for the Hubble constant. Well, I would have been more accurate than Edwin Hubble himself, but I probably would have been tempted not to publish my paper, thinking I did something wrong, because there's a big difference between 500 and 70. And this happens a lot more than we'd like to admit in science, where we get a value and it doesn't line up with the standard value, and and not for any bad reasons. We think we did something wrong because we don't line up with all the other tests that were done. But it might be that we did something right and everybody else did something wrong. And so there's this phenomenon called tracking where we tend to accept values that are closer to the more accepted value than the further outliers, which again is not a bad thing, but sometimes it could mislead us. Like it took several decades before the Hubble constant got to be close to its accepted value. And sort of along those lines, this second graph here, and this is a great article. I recommend you read it. But um, there were two main groups of teams here. One that were getting values around 100 kilometers per second per megaparsec for the Hubble constant, and there was another team getting values around 50. And so, as a community, that's a difference of factor of 2 that we didn't know what the Hubble constant was. Um, and and again, I see this probably there's a bit of tracking bias in these numbers staying together. Um, and so part of what the Hubble Space Telescope Key project at extragalactic distance was about was to figure out who's right. Is it 100 or is it 50? And it ended up coming to a value around 72. And for a while that was the accepted value, but we'll get further down that road here. But this is a really important lesson to keep in mind when we start talking about values of constants. You know, we have to watch out for things like a tracking bias that, you know, we don't want to be too far off the accepted value, um, which could play into some of the discussion that we're going to have here. Okay, so I said there were two methods. There's a lot of methods to calculate the Hubble constant. There's two main methods here in the crisis in cosmology. The first is more closely related to the work that I've done in the past, and that's looking at um, essentially expanding what Hubble did, looking at the expansion of the universe from, you know, in the nearby universe. Type 1a supernovae have been the weapon of choice lately for this. You know, a few years back, in 2011, I believe, the Nobel Prize in Physics was given for the discovery of dark energy using Type 1a supernovae. Um, what does that mean? Well, so the peak brightness of a Type 1a supernova is fairly consistent, and here's an artist's representation that the reason we think all of these are at very close to the same brightness is because they originate from very close to the same conditions. In this case, it's a white dwarf star with a giant star companion, and the white dwarf is, through gravity, is pulling material off its companion. Um, and at a certain point, when that white dwarf star gets enough matter, uh, when it's grabbed onto enough matter, when it's accreted, to use the 50-cent term, when it's accreted enough material, it becomes unstable under gravity, and that's when we get the supernova explosion. It's a runaway thermonuclear explosion. And so we think those conditions are the same, which is why the peak brightness seems to be the same. And so we talked about Hubble's law. That's if we have what's called a standard candle, something that has the same brightness, we can estimate distances using that standard candle. So in this case, Type 1a supernovae, Cepheid variables are another one, and there's a whole system. I'm going to cough. There's a whole system called the cosmic distance ladder, where We can triangulate to stars that are close enough. Cepheid variables are and standard candles, and then type 1a supernovae are standard candles, and so we can build this ladder rung upon rung, looking further and further out into space, measuring distance. But higher rungs depend on lower rungs being correct. Uh, so, like in the diagram that's shown here, if we can triangulate the distance to a Cepheid variable, then we can calibrate the brightness of the Cepheid variable with that triangulated distance, and then we basically got a calibration for all Cepheid variables. And same thing with a Type 1 supernovae. If we can find a Type 1 supernovae or supernova in the same galaxy as a Cepheid variable, then we can calibrate the supernova with the variable star, and um, and get that distance. So there's a lot of assumptions in there because these different distance measurements are all stacked on top of each other, and it's a little bit of a house of cards. If one of the lower rungs is wrong, it's going to make everything wrong, and so you got to watch out for that. And that's actually one of the things people have brought up as far as how do we fix this crisis in cosmology. The other method to measure um, the Hubble constant is to use what's called the cosmic microwave background power spectrum. So this is a picture of the cosmic microwave background. I want to say this is from the WMAP probe, but I'd have to double check. But this is essentially the background temperature of the universe. And from a Big Bang cosmology perspective, this light comes from when the universe cooled off enough, when it expanded and cooled off enough, so that light could now travel freely through the universe. Before then, the universe was so hot and so dense that a photon, a light particle, couldn't get very far without being absorbed or scattered by another particle or in the universe. And so, uh, from a Big Bang cosmology, when the universe had expanded enough, when it had cooled enough, now the photons, the light particles, can just travel basically infinitely from one end of the universe to the other, unless they run into something. But the the density was low enough that it was less likely for it to run into stuff. And so essentially, they talk about this being the smoking gun of the Big Bang, or um, the first light of the universe, or whatever. From a Big Bang perspective, this is the earliest back we can see in the universe. And so the idea of using the CMB power spectrum, CMB for cosmic microwave background, um, is that we look at these variations in temperature that are on this image, and they should correspond to variations in matter density and such. I think there's a nice image here on this big thing. Yeah, here we go. So here's the cosmic microwave background, and you see this little like vibration, this ring, and that's supposed to line up with this galaxy cluster in the picture. And so, using the measurements of the cosmic microwave background, models of how the universe evolved over time, and current observations of the universe, kind of putting those pieces together, you can get an estimate of how the universe expanded, and therefore the Hubble constant. And it turns out these two methods, the cosmic distance ladder, type 1a supernovae, and the cosmic microwave background, they don't match. And that is the crisis in cosmology. Um, let's see. So that is the Hubble tension. So we've got two different values of the Hubble constant. So early time measurements, that's the cosmic microwave background. From this article a couple of years ago, says gives us a Hubble constant of 67.4, and the late time, that's the supernova, gives us 74.03. It Depends on which paper you're looking at, who you're listening to, but more or less these are the values. Um, so that at first glance it's like that's not a big difference, right? I mean it's within what 10%, which is a whole lot better than a factor of two. But um, the problem comes in is when you look at these plus or minus numbers. So plus or minus zero point 0.5 for the early time measurement. That that is a measurement of probability. How likely this number is to be off that exact 67.4, and um, those plus or minus numbers say with random fluctuations and errors in the data, it could be off a little bit, but we only think it's off by this much. And in this case, zero point 0.5. And if you look at the late time one, it's plus or minus 1.42. Those aren't big enough numbers to get those two numbers in alignment. And that essentially is the crisis in cosmology. Um, these numbers, the difference in them is somewhere in the neighborhood of like 4 sigma. Okay, so sigma is um, how do I explain that? It's a standard deviation, and it's basically you know about 2 or 3 sigma. You expect even with the most random fluctuations in the data, you expect most of the data to be within 2 or 3 sigma. So being outside of 3 sigma is pretty crazy. And to put it in a different light, it's basically a 1 in say 50,000 chance that those two numbers are actually the same. They've just been affected by random fluctuations. A 1 in 50,000 chance. Like that's not good if you're trying to get all your cosmology lined up. You've got two measurements that basically don't overlap, and you can't explain it by just random noise. So I've gotten a little ahead of myself. I just want to go back, kind of in my grad school days. So right before, as I was graduating undergrad, this was kind of the state of affairs. So you got the mass density of the universe in your x-axis. You got basically the cosmological constant in the y-axis. And from all our different measurements, the different colors represent different ways of measuring the expansion of the universe. The blue there are supernovae. The green is the cosmic microwave background. You say they overlap in that little bitty spot, and this was for the supernova acceleration probe, or yeah, and as they were proposing it, so this was the state. They're like, we just want to narrow down this little spot here, and everything's good. But as time went on, you saw here's the green, here's supernova, and then these contour lines are when you bring in the cosmic microwave background. Um, okay, they overlap here, I guess. But over time, they started to separate. Here the yellow is cosmic microwave background, and the red is combining the supernovae and the microwave background. Oh, the yellow is the cosmic microwave background and something called baryon acoustic oscillation. um, which is another method to determine the age of the universe. And until finally, this is a nice summary chart here. Um, in 2000, you've got, so the blue is the cosmic microwave background, the red is the cosmic distance ladder, the supernovae. And you see back in the, from about 2000 to 2010, they pretty much lined up. And then as these error bars shrink down, we're these two values are diverging, um, until you're where we are today. And let's see. So this was from 2020. Yeah. So here's where I get the four sigma difference. Um, this paper in particular, though, looked at type 2 supernovae to measurement, and they got between a 1.7 sigma and a 1.4 sigma difference, which is more. 1.4 sigma difference is like a 16% chance that those two values could because of random errors are actually the same. They just look different. So it's still only a 16% chance. Essentially, the important ones are this pink peak and this orange peak. So the orange peak is the cosmic distance ladder. The pink peak here is the cosmic microwave background, and you see they're just these peaks. If the Hubble constant was the same for these two, they should overlap, and the more overlap they have, the more likely they are to be the same value. And you see they are very not overlapping. When some recent data from the James Webb Space Telescope came out, so it's in this with Wendy Freeman, who was one of the key figures in the Hubble Key project, that gave us that initial 72 value. Um, she's one of the leaders in this project, and basically came out and said, well, initially, before this paper came out, they said it was that their data had lined up with the cosmic microwave background and they had fixed everything and it's not really a problem. But now, between when she had kind of leaked that information and when they actually got the paper out here, I'm trying to find the graph. Here it is. Um, they found actually it doesn't line up very well. So this CCHP JWST is the new value that they came up with. The cosmic microwave background is this narrower peak, and you see they overlap a little bit, but still not great. It actually, if we had the supernova peak, it would be somewhere over here, and so it doesn't agree with either of them, which is even more frustrating. Um, and so this is the crisis in cosmology is we have these measurements of the Hubble constant that don't line up, and that as we get more and more precise with our measurements, they're actually getting less and less reconcilable rather than closer like we had all hoped, or astronomers had hoped. So what does it all mean? It means one of two things from a Big Bang cosmology perspective. One, there's systematic errors or biases in the data that are throwing one or both of the measurements off. So, like I said, with the cosmic distance ladder, maybe Cepheid variables. There's another factor in there that we're not taking into account. So the dust is something that a lot of times is pointed to as maybe being a systematic factor that would make that would throw off the supernova values or the cosmic distance ladder values consistently in one direction. poor calibration, crowding, and trying to find these Cepheids in a crowded field of stars. Maybe there's some error being introduced. They're obviously we're modeling how the CMB evolves over time. So maybe there's some problematic assumptions or something wrong in the model is going to drive that answer in the wrong direction. Um, so there's that. That's kind of the mundane answer. The answer that astronomers are more excited about is that maybe there's some new physics. Maybe there are, you know, dark matter particles interact in ways that are different, or there's uh, a new type of neutrino that has some interaction that this is the only place we've noticed it so far. Or maybe dark energy isn't as constant as we think it is, and it fluctuates way more. Um, yeah. So that all could be a possibility. Now, I've used the term "we" a lot because I was an astronomy student, astronomy professor for a while, but honestly, I find this very interesting because as a young Earth creationist, I don't think that the modern Big Bang standard cosmology is correct, and I think this is a way that it shows it's not correct. That as we get more precise, these values are going to get further and further from each other and less reconcilable. It reminds me a lot of what happened in the Copernican revolution. So right before Copernicus, it, measurements got precise enough to show the solar system cannot be geocentric. The Earth is not in the center of the solar system, but everyone assumed it was, and so they kept modifying their theories. So you have the term epicycle. But as we started getting more precise measurements, just a simple circular orbit for a planet was not good enough, and so so astronomers had to add these epicycles, so these kind of little circles on the orbit, and that would help to explain retrograde motion and some of the motion of the planets that just a simple circular orbit could not. And I mean, things got really complicated. Um, and this is part of what led Copernicus to try and put the sun at the center of the solar system rather than the Earth. Now, even Copernicus's model didn't work because the orbits aren't circular. It wasn't until uh, Kepler introduced the idea of elliptical orbits that we finally got uh, the simple math that worked for the orbits. And I feel like we're at the same kind of juncture here now with cosmology and this crisis in cosmology. I feel like we're starting to add more and more to the theory to prop it up. Now, to be fair, if you think a theory is true, that's not a terrible thing to do. But over time, if you keep adding knobs to the theory, if you keep adding variables to the theory, you're going to overfit the data. You're going to have so many things you can change and tweak that you could fit any sort of data. You can look it up. There's a YouTube video where somebody took epicycles and added them up in such a way that it traces out the face of Homer Simpson. Um, and again, it's if you add enough variation, enough things that you can control and tweak, you can fit any sort of data. So I think this is interesting. It's going to be exciting to see what comes of this. From a young Earth perspective, um, again, I think it reinforces that the Big Bang is not the correct model. But at the same time, like, how do we deal with it? How do we look at the expansion of the universe? Now, the Hubble constant is probably not the constant we care about, but we've got the expansion of the universe, we've got the cosmic microwave background. Like, how do we explain all of those things? Um, just real quick, for the cosmic microwave background, there's been some explanations over the years. Um, so one is that it's just dust. Let's see. That that what we see in the cosmic microwave background is just dust in our own galaxy. The problem with that is the cosmic microwave background is very smooth, and dust in our galaxy we know is not. And so those two things lining up is very unlikely. So um, dust from our galaxy, nearby, being part of the cosmic microwave background, I don't think that's a good explanation. Sir Arthur Eddington, an astronomer back in the 1920s, or astronomer back in the early 1900s, in the 1920s, he proposed this temperature of interstellar space, which was very close to what later was found to be the value for the cosmic microwave background. Some people point to this as a possible explanation. The problem with that, though, is Eddington's temperature, so it would come. Basically, the basic idea is that stars give off radiation and they go all throughout space. And so, if you were in a spot of empty space, you would have some energy from all of those stars that you would feel as a temperature. And so, it's just kind of diffused radiation in space, I think is a simple way to put it. The problem is, it has a different, that sort of energy has a different quality than what we see in the cosmic microwave background. To use the bigger scientific terms, is the cosmic microwave background is a black body spectrum. The simple explanation for a black body spectrum is if you had something that was perfectly absorbing of energy, so it absorbed all the light that touched it, you'd heat it up and it would give off energy in the form of heat and light as well. And it would have a characteristic shape called black body spectrum. Um, and what we see is, because of the way Eddington set up this diffused radiation from stars and dust and things, it would have a very different characteristic than a black body spectrum. And so, again, not likely the explanation for a cosmic microwave background uh, from a creationist perspective. There's been uh, other explanations. Um, Russell Humphrey has his white hole cosmology. I think there's an explanation he has in there. Um, Danny Faulkner talks about the rakia. It's the term for the firmament, and that it may be something characteristic of the firmament. But again, these to me feel kind of forced. And so this is one of the areas the young Earth creationists really need to work on too. Is like what is the cosmic microwave background? How can we explain it? All right, I think I have rambled on long enough. Thank you for joining me for Theater of the Cosmos Coffee, and until next time, keep looking up.